You're going to hear this described in different ways. I rarely call it a committee machine. I don't know. That might be a more engineering term. Ensemble methods is generally how I coin these things. But what it's going to be doing is thinking about gathering information from a bunch of different classifiers. And those classifiers are going to be essentially on the same model, just different fits. Okay, so that's going to help us quite a bit in the next couple of weeks. So I had hoped to start with random forest right away, but I need to tell you a little bit about boosting first. So I'm going to talk about boosting and the most simple boosting method, which is add a boost. And then we're going to get into random forests. And if time permits, I will go into gradient boosting, which it probably will, but not today. I might have to save that. So I want to come back then to our central tasks. We want to lower the generalization error, which we're going to aim to do by reducing the bias or the variance or both. Okay. And we know that bias and variance are not as clear-cut in classification as they are in regression. If you think about that picture we looked at a couple of times ago when we were together about the bias and variance and the prediction error for regression and classification for KNN in one column and linear regression in the other. We saw that right away. And so we're going to be talking about variance. You're going to hear me talk about it in two different ways. First of all, you have the variance from the data. And you also have the variance in terms of the model itself. In particular, the variance that is linked, I wouldn't say variance, the variation that is linked, that is a result of instability. I've already alluded to instability, where it comes from. Small changes in the data or the model fit can lead to huge responses in the response variable or in the model itself, the structure of the model in the case of the tree. So I could have, and it can arise from the situation that I keep describing. One split is really good and the other one's really good too. It's just a tick worse, right? We're giving totally different trees. Or they could give the exact same result, the exact same tree, arising from different structures. This happens also in Bayesian inference too. If we think back, or if you think ahead, we're going to talk about graphical models. Those of you that were with me in the spring will know already that different graphs can give the same exact likelihood, right? So we have likelihood equivalent models. We have goodness of fit equivalent models. But this is an issue. So there are some methods that are known to be more unstable than others. Trees obviously are one of those methods. The other one is the neural network, which we're going to talk about in a few weeks. And then we have other methods that are known to be more stable. Linear regression, LDA. These things are kind of known to work well. But there's a lot of assumptions. Obviously, unless you have Gaussian data, you can't do LDA. And you may really need to interpret your model well, so you may not even want to reach for LDA. You may want to go to logistic regression, but you have too many categories in your response variable for it to work well. So maybe you're just stuck with CART, and then you have this problem. Okay, so there's a lot of things that need to be considered when you select your method, obviously, but this is an issue. So let's talk about the hierarchy of methods, okay? Because everything we're going to talk about now is going to build on the tree stuff. Although boosting is a general method that can be used with any classifier, we're going to talk about it in the context of trees. So classification trees, you've got bagging, okay, which is, we've talked about the bootstrap before. It is a way of bagging trees, or bagging any classifier, can be used with anything. Random forests, which you've read the paper now that was in the Journal of Machine Learning. Your book actually covers random forests. I don't think they do it the same justice as the paper does, so we went to the paper for that. So that's a really smart way to average trees. And then boosting is sometimes regarded as the smartest thing going. And, in fact, just to put it into perspective, in years past, I've had students, enter these data competitions, in particular as a final project idea, and I always hear about boosting. Everybody's doing boosting on Kaggle, I guess. There's other more sophisticated methods that are way better than add a boost that people are using. So lots of things coming out of boosting still. So still a very hot area. This is going to help improve performance, but it's not without cost, okay? We're going to see that we're going to lose that beautiful model interpretation that we had before. Okay, so here are some things that we know. Trees can handle big data sets. You can have mixed predictors, which is important. We can't do that in LDA. We can ignore variables. It has elements of feature selection inherently in the search for different splits. Clever ways to handle missing data, and very easy to interpret, especially with small trees. And there's some downfalls. Large trees are hard to interpret, okay, especially if you have many different ways to different categories. Predictive performance can be poor. In fact, we'll see, even when we get to the random forest paper, that they kind of stink in terms of predictive performance. So unless you have a very good reason for going to them, it's probably more on the side of model interpretation. So these are some issues, and so there's ways to kind of make them better. And bagging and boosting is one of them. These methods exploit instability, and they do it in a way to create better accuracy in the model. And both of them are very similar, okay, in the sense of what they do. They operate by perturbing the learning set. The learning set is just the training data, okay? So again, there's a little bit of clunky terminology that changes from chapter to chapter. But learning set, training data, we're kind of changing it in some way. But there are different ways. Every perturbation of the learning set is going to generate a different classifier. These are going to be thought about collectively as an ensemble, okay? Or think about the individual classifiers as base predictors or base classifiers, okay? So taking this training data and changing it a little bit, and then fitting a classifier, fitting another one, and then aggregating over these different classifiers, these base classifiers, is going to help stabilize the solution. The ensemble is combined appropriately, and we'll talk about some different ways there. And it's more stable, okay? And success of these methods depends on the degree of instability. So if you have a method that's doing really good, you might not gain much by doing one of these approaches, okay? But if you have a method that's doing really poorly, we'll talk about boosting, it miraculously can improve things. This is called ensemble learning or committee machines, okay? Now, in general, boosting is regarded as the most powerful method. Random forest is next. Bagging, not really great. And the single tree is just like, that's really bad, okay, in terms of performance. But when I talk about performance here, I'm talking strictly about accuracy, okay? I'm not talking about, if I want to interpret the model, Again, we have different reasons for going down different avenues. So classification trees can often be noisy and problematic. So these are the three different methods for committee machines. One is bagging. And if you think about bootstrapping, what are you doing to the data? Okay, you're resampling the data with replacement. And you're generating new data sets, bootstrap data sets, that are the same size as your original data set, okay? And what we talked about was, well, let's fit a classifier and figure out what the prediction error is. And let's find another bootstrap data set, fit a classifier, find out what the prediction error is, and do it again and again and again. Okay, we talked about doing that as a way of kind of estimating this prediction error. And that had problems. It had an over-reliance on the training set. We had to make some adjustments to the estimates in order to account for overfitting. But I said in general, bootstrapping is a very powerful paradigm. It can be used in many ways. That was just one of the ways. Okay. And I also said you can bootstrap a mean estimate, a confidence interval, all different types of measures, and you can also bootstrap the actual predictions. Okay. And that's what bagging tends to do. It takes your original training data and it resamples it, and it gets your y hats. Okay, and then it does it again. What are your y hats in the next bootstrap data set, and what's the y hats in the next one? And then it's going to aggregate them. The aggregation can be done in a few ways. You know, you could kind of think about weighting the different classifiers if they're good or bad. Maybe one bootstrap replicate does really good and one does kind of poor. So you could do something sophisticated like that, or you could just average things, average the predictions, use majority vote classification, or just the mean and regression. So that is very straightforward. Boosting, so the perturbation here is that I'm taking different realizations of the training set, different resampled bootstrap replicates. That's kind of the perturbation of the training set. It's a resampling procedure. Okay? So I'm creating big B different data sets. Okay? And I'm moving from there. Boosting does something completely different. Okay? It takes that training set and it never resamples it. Okay? It just works with the training set, but it weights things differently in the next iteration, and it weights things differently in the next iteration. So it's making changes directly to the training set in an iterative way, which means the kth change depends on the k minus 1th change. Okay? It's just building consecutively. And it's going to kind of do classification by majority vote. So we're going to go into details about this one. But they're totally different processes. It's very important that you have these distinct ideas in your mind. We have reweighting, the iterative process of changing the data set. And then we have the bootstrap replication. And random forests is more similar, of course, to bagging. Okay? It relies on bootstrapping and resampling in two directions. Okay? It's going to consider resampling the sample points, but also considering random subsets of the predictors for the splitting. Okay, so that's going to be a whole other animal. But we're going to start with boosting. Okay, this is the comparison here. Bagging, we're randomly doing independence from the training set. Boosting, we're reweighting, just like I said in words. What do? You fit the model. Okay, you fit the model in both. One is designed to reduce the variance. One is designed to reduce the bias. They both, okay, so this particular approach, in the end, I mean, we try to balance these things out. This one is more effective for bringing down this prediction error. Okay, so this is actually designed to do that in such a way, in particular in this step. This one, not necessarily. Okay, so that's kind of the framework here of the two approaches. Bagging is sometimes referred to bootstrap aggregation. This is one of the original committee machines. Now here's the thing. If I'm trying to strengthen my classifier, and I have my training set, and I'm looking kind of, and it's pretty good, okay? Maybe my prediction is pretty good. I use cross-validation or something like that. So I think, well, let's try to do bagging, okay? And so I'm doing this bagging procedure, and I'm getting all of these data sets, and I'm going to average the prediction. Well, I mean, if the classifiers are not too different and they're not giving such major results, you're not going to see a major increase in accuracy. You may see some differences, but essentially, if you're averaging a bunch of foolish things, you're going to get something foolish. If you average a bunch of things that are really good, you're going to get something good. So the diversity of the classifiers and the performance is going to directly impact how much you gain or lose by doing such a procedure. And this piggybacks on that idea. If you do something really bad, you could, end up with something really good. Okay, but in bagging, that is less observed because of this, obviously, this over-reliance in the training set. That's less observed than with boosting. Okay. So suppose you have a classifier CS of x, and now I'm going to talk about this in general. We're going to think about it with respect to trees, but you can bag anything. And we have kind of a label coming from the training set and different points. All we're going to do is draw bootstrap samples in the same exact way that we did before. This was the nomenclature we used before by big B here. Each one is going to have this data of the same size as n with replacement. And then my bagged estimate is going to be the majority vote over all of the bootstrap classifiers. Okay, so all right, so say I am a sample point, okay, and I'm doing all of this bagging. Well, I need to kind of figure out what my final label is going to be, because this classifier is going to tell me something different, and this one, and this one, and this one, and this one. So I need a way to kind of aggregate these things. Gets a little sticky because, you know, I may be included in bootstrap sample 1, and I may not be included in bootstrap sample 2. You see? So I kind of have to take care a little bit and interpreting what my final outcome is going to be. Okay? In other words, do I really want to include all of the points for which I participated as a training point? Okay, so if I was collected 4 times in my bootstrap replicate 1 and 0 times in bootstrap replicate 2, my label from bootstrap 2 is going to be more valuable, right? Because I was not included. I'm effectively a test point. Okay, so we're going to crawl into some ideas about that right now. But for simplicity, let's think about it as a majority vote over all the classifiers. We're going to talk about something specific called out of bag, which is a very powerful idea that will allow us to consider these aggregates over the out of bag samples. All right, so now if you think about this, I'm going to collect my label over all of these different classifiers, but if it's a tree, what does that really mean, right? So I find out I'm high risk, low risk, high risk, low risk. These trees are completely different structures. Okay, so how can you aggregate the trees themselves? And the short answer is you can't. Okay, you can't summarize the different structures. People have studied this problem, and it's not really solved at all. So that's the issue. But you can sure get a better label by doing that. But you have no way of consolidating the tree structures. This is an example of a bagged tree, an original tree. And these are some different bootstrap trees. They all look the same, but they're slightly different. If you look at the labels here, they all have different splitting rules, and they all have different proportions of points that are landing in the different pieces. And some of them are really problematic, I suppose, because in this one here, I don't see any ones being predicted. Okay. But other than that, I don't see any major glaring issue. So, you know, we don't really take care of looking at every single tree or every single classifier very carefully, because you're going to do this process to infinity as long as you possibly can, right? So you don't really have good control of that. But you can certainly imagine sprinkling samples down each of the tree and writing down their labels, 0 or 1, 0 or 1, and then at the end of the day figuring out which one is having more confidence or support. Just a couple words about random forest before we get into it next time, probably. It's a refinement of this process. You're going to do resampling as you would for bagging. The fundamental difference is that you're going to consider at each split a random subset of the features. Okay, so, you know, if you have 1,000 data points and 50 features, 50 different x's, okay, you know, you're going to bootstrap your data set in the same way as usual. You're going to do it with replacement. You're going to have another data set that's 1,000 rows. But now at each split in this tree, you're only going to consider, maybe you only want to consider 10 features. Okay? Randomly selecting 10 features and deciding which one to split on there. And then you kind of move down and you randomly select another bunch of features and so forth. So it's crazy because it thinks about resampling in 2 different directions. Okay? But it works quite well. And we'll talk about this next time with respect to out-of-bag stuff and correlation, which also speaks to the idea that bagging, you might not see a major difference in terms of performance because the trees might all look pretty much the same, or in terms of the predictions. Okay, so this is from a book that I have on boosting. And I like this quote: "How is it that a committee of blockheads can somehow arrive at highly reasonable decisions despite weak judgment of individual members?" And at this time, I think that we were kind of like in this budget crisis here. "Garnering wisdom from a council of fools." Okay, so you have a bunch of very weak classifiers or very weak inputs, and you somehow need to come out with something strong. Okay, so it's very actually surprising that such an idea could work. But this is, in fact, if you think about committees, I have to sit on a bunch of committees. It's awful, right? But if people had to make decisions on their own, it could be very dangerous, right? Somehow the committee, we kind of even each other out. I've got, I'm sitting with one blockhead and 3 kind of okay people, and, somehow it averages, okay? This is the exact idea, the principle that is a reflection of real life. Wisdom is defined in this context as accuracy. Fools are defined as the individual classifiers. Okay. So we're going to be actually combining a bunch of weak classifiers together to get a small one. They're going to produce a committee, a powerful committee. It's fundamentally different in the ways that I've already described, but I want to tell you these things because I think that boosting is actually a very, very important method, and it's one of the most highly regarded approaches to classification. These are from 2 very heavy hitters. One of the most powerful learning ideas introduced in the last 20 years. Okay, this is the guy this is your author of your book. This is the guy that came up with random forest. Also was at Stanford and has since passed. Best off-the-shelf classifier in the world. So these are not comments to be taken lightly by these 2 individuals. This is a really very powerful idea. So how does it work? I'm going to explain it to you in the most simple form, and it's called, it's this AdaBoost. It was one of the very original boosting algorithms. And since then, there have been, this tremendous advances. And so if you're interested in such topics, this book that I have, this is the guy, this Shapir. He's the one that came up with AdaBoost, and he wrote a very elegant book 2 years ago, I think it was. So there's a couple of problems. One is that you can only consider a 2-class problem. Okay, and we're going to have the same issue when we come to support vector machines. You can consider a 3-class problem, but you have to play this weird game where you kind of end up lumping classes together and making it into a 2-class problem. So conceptually, I think it is a possibility to do, but it's not really considering 3 classes the way they should be, or more classes. The other thing you have to do is typically we always use 0, 1. 0, 1 class, 1 the other. Here you have to actually use -1 and 1. And the reason is we have to determine the sign. Okay, the sign is going to tell us a little bit about the error. The product, the sign is defined by what we call a margin. The margin is going to be the product of the true y and the y hat. Okay, and so that's going to tell us a little bit about the sign here at the margin. Are we right or are we wrong? If we're right or wrong, we're still going to impose some kind of penalty for being right or wrong. Okay, obviously, if you're wrong, you're going to have a stiffer penalty. If you're really wrong, you're going to have a much stiffer penalty. So that's the approach that this is taking. That's why we need this -1 and 1. And the error rate is the same as usual. Okay. So how do you identify a weak classifier? Well, this question came up in my office this week, actually. I think it's a really good question. So one thing is that you never know how good you should be doing. Okay, so you have a data set. It's just a data set. And maybe you have 80% accuracy. Is that good? I mean, can you do better? I don't know. Maybe if I collected a bigger population, I would see something different. Or maybe it's, we don't know. Maybe if I used a bunch of different methods, I could see something different. Maybe I need to do something nonlinear. We don't know. That's why we're always looking. But we can kind of estimate how well a classifier would do if there was no signal in the data. And we started to allude to this when we talked about the Bootstrap 0.632 plus estimator. So we needed to think about, what if there's no information in the data set? Okay. If there's no information in the data set and you have two groups of equal size, then you would expect the error rate to be about 50%. Right? You're just kind of flipping this coin, or you're kind of deciding at random between the two labels, and you have balanced classes. You would expect, maybe you're right half the time. Okay? As you start to change the balance of the classes, that number will change. Depends on a lot of things in your data. But you can estimate what a no information rate would look like. What would no information in the data set look like? And the way you would do that, one way that would preserve the distributions of your features is to randomly permute the columns independently. Okay, so think about that. So if you have a row of data, an individual in your data set, and they have a profile, you have another individual, permuting the data just means mixing it up. Okay, just mixing it up. Obviously, you wouldn't mix it up all together because it would be the same data set, just moved around, different rows. But if you break the relationships between the features, okay, then you're breaking all the signal. Okay, so if I permute x randomly and I permute x2 randomly and x3 randomly, I'm generating a situation where I have no information in my data, or close to no information in my data. And if I fit a classifier to that, I should look at that accuracy and say, oh, 60%? I'm only at 63. I'm almost doing this is almost as bad as random. Okay, there's very little information in my data set. So when that is the situation, boosting actually is at its best, okay, which is somehow surprising. So it can take this garbage and make something good out of it, okay? So that's how you would identify a weak classifier. Now, that is not to say that this is always a point of confusion. Boosting can work in situations where you have a good classifier too. But it's always nice to know how far off you are from being random. Okay, so that's a useful exercise in general. And boosting will have the biggest effect if you have a weak classifier, because it has more to gain. Okay? Starting from a lower value. If you're starting already high, I mean, what are you going to do? You might be at the ceiling. Okay, so it's hard to say, but it's well suited for these things. So what is add a boost? The idea is that you sequentially apply this classification algorithm, the same one, repeatedly to modified versions of the data to produce a sequence of weak classifiers. Crazy. You're starting with the training data. The perturbation, you're going to fit a classifier. Then you're going to make a change to the training data. You're going to fit another classifier, another change, fit another classifier. So you're taking this data and you're making changes to the training data directly. And you're going to get a sequence of classifiers. And then, at the end of the day, you're going to take all of this information and create a prediction. In this case, I'm doing the sign because I have this -1 and 1. But I have all of these. This is a summation over all of the different boosting iterations. And then I have here a parameter which I'm calling alpha. This is the weight. This is a weight, and it's calculated in the algorithm in the boosting iterations directly. It's a function of the accuracy. So if a method is starting to, it starts off very weak, it's going to hopefully get stronger and stronger and stronger. The weight of that prediction is going to increase. Okay, so we want the stronger classifiers to mean more when it comes down to averaging these different things together. Okay. All right, this is what it looks like sequentially. You have your training sample just like described. You're fitting a classifier. You're making a change to the training data. This change actually comes in the form of weighting individual sample points. Okay? You're fitting a new model. You're doing weighting again, but that weighting doesn't depend on the original training set. It is recursive in the sense that it's depending on whatever happened here. Okay? So this is the idea here, and the weights, we'll talk about those in just a minute here. They'll be more clear. Just like I mentioned before, when you're putting the predictions in some kind of a summation, you want the good things, the good, accurate classifiers to have more weight than the garbage ones. Okay? So that's what that alpha parameter will do. There's another weight in boosting, and that weight is specific to the training sample. Okay? And it comes into play because we want samples that are being misclassified to be penalized more. Okay? I talked about loss functions and, if we want to prefer certain errors and stuff like this, and we have to do this cost matrix. It's a similar idea in the sense that we're kind of weighting these training samples. Those that are making mistakes are going to pay a price. Okay? And those that are really making mistakes, they're way off the margin, are going to pay a steeper price. Okay? So it's, in a way, getting around this issue that we had with the misclassification rate, how crude it was. So we're going to show a few different loss functions for doing that. But at the initial step, we're going to say, without loss of generality, all of the weights are equal. Okay, 1 over n. These are for each individual training observation has a weight of 1 over n. At each iteration from there, these observation weights are individually modified, and the classification algorithm is reapplied to the weighted observations. Okay, so these are where the two weights are coming from. You've got the alpha, which is coming from the classifier itself, and now you've got a second weight, which is WI, which speaks to the individual sample points violating the decision boundaries. Okay. And this I have already said in words. Those that are misclassified are going to pay a penalty. Okay. So this is what the algorithm looks like, and I'll just walk you through it. The initialization is, as I discussed, 1 over n. For 1 to m, you're going to fit a classifier. You're going to use your weights. It's initialized as 1 over n. You're going to compute the error. Now, this is going to give the error of the classifier. Okay, so it's going to, in this case, of course, the weights are going to play into that, the individual weights. Okay, and I'm summing over all the training set observations, and I'm looking for misclassifications. Okay, and this is summed over all of the weights. So this is giving an error rate. Okay, it's an error rate that is weighted by the individual observations. And then from there, I'm going to compute an alpha m. And this alpha m is going to sit on each classifier as being, a weight which is saying how good this classification is. So it is a function, of course, of the individual classifications that are weighted. Now, this alpha m, we're going to just kind of put it aside. Okay, nothing that has to be done with it yet. Then I'm going to update my weights, and I'm going to update them in a way that we haven't really thought about yet. Okay, so this update, I don't know about this nomenclature, but the new weight should be the old weight, okay, times, this is an exponential, okay, and it includes alpha, okay, times this kind of misclassification index here, okay? So this is going to be the new weight. And the output is going to be the sign, if you will. So you're going to do this over and over and over, updating the weights at for every training observation, you update the weights. And you compute this alpha for every classifier. And then at the end, you have this final decision that is being made. So this is the simple AdaBoost M1. There's other different AdaBoosts as well. So let's kind of look a little bit. We're going to bring that back up in a few minutes, but just to give an example. So this example is from your text. You've got 10 features, and there's 2 classes, and it's this combination of features. It's a summation, which is going to be 1 if it's above this chi-squared value with 10 degrees of freedom, and -1 otherwise. And I guess one of the points is you have 10 different features, and one thing that I didn't have time to go into with the trees is that when you have this true linear combination underlying the model, the CART method sometimes has a difficult time capturing such a thing. So the performance in the tree is expected to be kind of poor here. So the result actually from a tree is 45.8% accuracy. So it's pretty bad. And if you do a random in the exercise I just described by permuting things, you'll get 50%. So it's actually just worse than random. So the result is this single stump, and I said the accuracy is 0.47. This is the value here. Now, if you grow the tree super deep, okay, so this is a 244 node tree. You're growing it super deep. You're going to get down to about 0.25. Okay, so you might be overfitting at this point with this particular tree. But you're at, obviously 244 nodes. So if you are to do boosting, since it's an iterative process, you're starting at a very weak classification, right? And you're going to go to the next one. You're going to do this procedure, and you're actually going to bring this test error way down by a factor of 4. Okay, so this is the test error at the end. So it has tremendous value in this particular situation, although it's contrived, and we know actually, though we didn't discuss it, that this is setting up for failure anyways with a regular tree. But this has the power to really improve it. Okay? Okay. So your book goes into a little bit of a tangent on boosting and comparing it to an additive model. Of course, I think it's natural. We didn't talk about basis expansion, so I'm not going to go into a lot of detail here, and you're not responsible for this piece, but I think it's just kind of, at a glance, valuable to understand that it is an additive model, obviously, because you're aggregating over different classifiers, whereas you would be aggregating over different basis functions if you were thinking in that direction. So it's the same idea. So I think I'm going to skip through these things then in order to get to the random forests. Yeah. So it can be thought about in that we didn't talk about this particular topic. And it's just kind of sitting in my slides from last year. Okay. But let's get right to the loss functions. Okay. So how does this actually work that we can really improve things? How do the penalties actually work in practice? So this is the loss function that we're going to use. And so if you think about this loss function, it looks quite different than anything that we've used before. And when you have a two-class problem, of course, if you think about the exponential function and its shape, right, it kind of goes through 0, 1, and it shoots off to infinity pretty quickly. So, what we want, so if we think about y and f of x is being my prediction, y is being my true value. If they match, right, and then are negated, we're in a good spot. The loss is going to be small, right? So if they're both minus 1 times minus 1, and then you have a negative on top of that, right? We're in a good spot. Or if they're both positive, we're in a good spot because this is a negative exponential. But if they mismatch, then we're on the other side, okay? So it's easy to think about that, but the question is how to kind of control that, okay? But this is the loss function. And actually, we're going to use this loss function again. This right here is actually referred to as the margin, okay? Because it gives some value in terms of how far off you are from being right or wrong. So the basis functions, or the individual classifiers, because we're not really going there, have the values -1 and 1, okay? And so that's actually critical to understanding this. And it ends up that the problem that you're trying to solve here is to infer, if you will, if you think about it with respect to a basis function, the betas, the coefficients, and the predictions from the individual classifiers. So here they talk about it with respect to a basis function, which may confuse you when you're doing the reading, but really the coefficient, we've just talked about it with respect to alpha, and it is the same thing. Okay, they just try to recast it into something that people may think is more familiar. Okay. All right. Now, this can be kind of thought about in this way. If we let the weight be this exponential loss function, it's going to be, first of all, it's at iteration m. It's going to change at every iteration. And it's for the ith observation. It's going to be individual specific to the training point. Each one of those training points is going to have a weight, and that's going to be computed using this margin. Okay? So this is the prediction of the model, and this is the true value. And so we can think about it, although they've been talking about it with respect to an additive stage-wise model, which is a little confusing in terms of reading the text. You can think about it in this context. We've got individual weights, okay? And then we have pieces here that are describing the margin and the prediction. Okay, so this is going to tell us, this is going to give us the penalty, essentially, we need to kind of do what we want to do in terms of penalizing those severe points that are out. But we need to infer these different parameters. Okay. Now, so far, so this is the first time we're dealing with exponential loss. I think the margin is pretty straightforward. We're going to see it again when we get to the support vector machine. But, this is, again, boosting iterations. And there's a major difference between misclassification rate and exponential loss. And this is the training data. So I know we wouldn't really do selection based on training data. But we see major differences here. In particular, the misclassification rate on the training data dives to 0 after about 200 iterations, whereas it's going down. It's still going down. It's got much more to go. It has the same shape, but there's still more information. This tells me that this model is not really doing anything different. Right? Is it 0? It's just kind of like tanking out. The training data is used up. Here we have something that it is recognizing this quantification of this margin is helping us kind of carry this a little bit further. And although we're not looking at test error here, we do see already the differences in the model. Okay, I'm going to skip that. Okay, so, in classification, the margin plays a similar role than that the residual plays in regression. This is what the margin looks like. I've already described it in the earlier slide. So, of course, we know that if we have a positive margin, we're correct, and if we're negative, we have a problem. So we want to kind of use that information. Okay, we're using that, and we're using it in the exponential function, but we have other options, right? Other things that we can do to work with that margin. But the goal of this method and the support vector machine is to produce positive margins wherever possible. And any loss criterion should penalize negative margins more heavily. And so that's also something fundamentally different. If I asked you to think about this problem and to tell me, what would you do? You would penalize the ones that are, severely misclassified more. And if you're closer to the decision boundary, you'd still be penalized, but maybe not as much. But if you're right, maybe you wouldn't impose a penalty, right? So if you're really right, maybe you wouldn't impose a penalty. But the nature of the functions, it doesn't exactly work that way, okay? Because of the nature of the exponential loss, okay? But nonetheless, it should be monotonic, okay? So, the worse off you are, the more severe, and then it should kind of creep down. The closer you get to the decision boundary, eventually you might get some nominal penalty, right? Because, of course, if you're right and you're close to the boundary, then you're close to making a mistake. If you're really off the boundary, you shouldn't suffer, but you will based on these functions. So that's one of the issues, and this is a really important plot, and it's in your textbook. On the x-axis, you have the margin, and then you have the loss function. So I mentioned this is correct, right? So let's start, I think, with misclassification, okay? And so for misclassification, of course, a negative margin means it's misclassified, so you have a 1, okay? And then once it's positively classified, you have a 0, right, in your loss function. Okay, so if you're, that's how we compute the misclassification rates. Where do they not match? That's where the penalties come. But that's very crude, and we know that. So it's flat, right? It's flat. And if we're going to use the information about the margin, we need to do better than thinking about what side it's on, okay? And so these different profiles do that. And so, again, if I asked you to think about this, you might say, well, why don't we just use what we use for regression? Okay, I mean, we can do that. And so this is the red line, which says we have squared error, okay? And yes, I mean, that works a little bit, right? I mean, when you're wrong, it's still going in the right direction. So what does this mean? This is the margin. Well, if my margin is way out here, I'm super wrong, okay? I mean, that's really wrong. And my penalty is going to be higher, okay? As I start to approach 0, I start to get close to the boundary. I'm almost right, okay? So the loss is going to go down. And that is true for squared error. But, as I mentioned before, by the nature of the margin, we also have penalty here when things are correct, okay, which is counterintuitive, but it's the nature of the loss function, okay? And it does provide some value because points that are 0.95, I'm sorry, 0.0001, okay? If they have a margin that's very, very small, they're very close to being misclassified, okay? And so they should be penalized a little bit. We have to kind of make sure that they're going to stay on the right side of the boundary. So that should, in fact, be true. And as you get more correct, you have less of a penalty. If I think about this as my loss again. But the squared error will actually turn around. Okay? It's going to turn around, and then we have an issue. So it doesn't follow this monotonic expectation that we would have about how we should assign penalties. Now, exponential is the blue one. And what you see right off the bat is that it has the monotonic property, but it's pretty rigid. Okay? It's pretty stiff because, look at how steep this growth is on this side, right? I mean, it's just shooting up, 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 up. And so points that are out here are going to be very, very large. Okay, so it applies a very stiff penalty to those that are not being classified correctly. The binomial deviance and what is used with the support vector, which we'll talk about, that is a little bit softer. Okay, it's a little bit softer to the point where, these points that are really misclassified pay a price, but it's not out of scale, right? Because if you follow that blue line up, if you have points that are way out, that's going to be a huge value. And what does that mean? It means that I'm bringing in this huge weight into a classifier, right? I'm calculating, because at every time I'm updating the weights, and that weight depends on that loss. And that loss depends on the margin. And if every time I have this crazy point, or maybe 3 crazy points that are out here, and I'm assigning this very large weight to them, then I'm driving the classifier toward my outliers, potentially. Okay, so this is a very sensitive process to outliers, obviously. Okay, if you have some that are very, very different, super misclassified, they're going to kind of take that classifier as you iterate through the boosting iterations and hijack it. Okay, so we have to be careful about that. And the binomial deviance and the support vector are less, it becomes less of an issue because it does not have this severe takeoff. Okay, so this is a very important plot to think about. So this is exactly what I've said already. 0, 1 is not good. Exponential and binomial loss, comparing them about the degree of misclassification. We have situations with the loss function if you have mislabels and stuff like that. So what if one of your points is mislabeled? What if you have somebody that's low risk that should be high risk and it's just an error, right? I mean, these things can really drive such an algorithm. So one has to be very careful in processing the data also that you have something that is very clean. Okay. All right. So I'm running out of time already, so I'm kind of move a little through this and highlight the major points, I think. There's a relationship, obviously, between squared error loss and absolute loss, like we would expect. It's a similar and analogous relationship between exponential and binomial deviance. Okay, so these things are true. Squared error loss places more emphasis on observations with more residuals. So if you think about the plot, which I'll show over here, here's squared error loss. It's kind of putting things in a more severe penalty in terms of loss. Absolute loss is a little bit less. A similar relationship to the one we just saw with the classification regression against exponential and binomial deviance. Okay, similar thing. There's kind of a go-between called the Huber loss, which says, okay, well, if the difference is greater than a value, I'm going to use, if it's within reason, I'm going to use its loss. If it's really outside of what I would want to use in a loss function, I'm going to use something different. Okay. So that's the Huber loss. It essentially it shares properties of the squared error loss, which shoots off too fast, but it kind of tames it. But it also makes it such that we don't have a discontinuity at 0, which can be a problem when we go to optimization techniques. Okay, so there's other loss functions. There's tons and tons of loss functions to think about, but these are some of the major points. Okay. So I think the last thing I want to do is, in just a few minutes, discuss this table, which is in your book. I think it's a really nice table, because we've talked about now AdaBoost. I'm going to talk about AdaBoost next time when we discuss random forests. As further motivation, we'll revisit the algorithm, because it is a little sticky to think about that. So we will think about it again. You will have practice using AdaBoost. It's a very expensive method. It's a lot of computational cost associated with doing those iterations. So we've talked about some different methods. I just wanted to kind of show you this because this is the way I like to think of things. We haven't talked about these methods yet, neural networks and support vector machines. We will. These are topics on our agenda. We have talked about trees. Mars is very similar to trees. We've talked about KNN, but not kernels. So we've done a lot of things here. We're going to keep moving in this direction. But when you think about, because now we're really kicking into high gear. We're doing methods that can handle both regression and classification. There's different things to think about. Is it a two-class model? In other words, can I use boosting, or do I have to do something funny to the response variable? Do I have multiple categories? So now we're getting into the finer details of things. Is there a lot of missing data? The questions are really endless, and so you really have to understand the ins and outs of the different methods to think about what's appropriate. Because in real life, your boss is going to give you a data set to analyze, and you're going to have to know what to reach for. So I think this chart is very useful. I look at it and I think, okay, this is really useful. Think about it. Mixed data types. What if you have continuous and categorical predictors in the same data set? Okay, you can't use discriminant analysis. Okay, there's automatically things that you can't use. You can't use many of the other methods that we haven't talked about. You can use trees. Okay, you can't really use KNN because you have to decide on a distance. Okay, and the distance of mixed data is it's unresolved. Okay, how do you quantify distance between categorical data when it's mixed with continuous? If you have missing data, so I already talked about trees as an issue, as resolving that, and kernels also can handle such things. But there's lots of things to think about. What if you have massive sample size? What if you have irrelevant inputs? What if you have features that you don't know if they're useful? You've got tons of features and you don't know what to do with them. Trees are going to grab that information out. So these are the things that you're thinking about, and always these are the two that I harp on all the time: interpretability and predictive power. These things have to be balanced, and it depends on the domain that you're in. But you should really be thinking, which was one of the objectives of that one concept quiz, understanding as we go through the high-level ideas and which methods are best suited for different types of data sets. Okay, and so on your third homework, still I'm kind of holding your hand and telling you what to use. You're going to have one final homework where you're going to be more or less set free to analyze these data sets, and it's going to be up to you to not only choose the appropriate method but apply it correctly. So really having a command on the different approaches and the different nuances of them is going to be important.